Go? Yep. Okay. Well, thanks for joining us, everybody. I'm going to talk about continuous quantum walks. There's nothing particularly new. It's a bit of an overview and introduction, although I'm not going to be taking too many hostages. Okay, just want to go to the next page. I artificially broke it up in 3 parts. I'm going to start by talking about some algebraic graph theory. People get a bit worried about the physics, and so we'll put the physics off for a bit. And so I just want to talk about some old results in algebraic graph theory. And in particular, this is probably one of the first results you would come across in spectral graph theory, that if you've got a graph of diameter d and exactly r distinct eigenvalues, then d plus 1 is less than equal to the number of distinct eigenvalues. Okay, so it's a simple bound, and it's kind of interesting. And what I want to do for the first part of this is derive something which is not quite an extension, but if you look at the proof, you can find a common generalization of what I'm going to prove in this result. So we're just looking at a eigenvalue bound on a graph theoretic property. One corollary of this result, just to prove it's not entirely trivial, is it follows that the eigenvalues of a path are distinct. So a path got on n vertices has got diameter n minus 1, and so you get equality. So the eigenvalues of a path are distinct, so it's not completely useless. Now the bound I want is not on the diameter, but on something which graph theorists usually call the eccentricity. And so it's just, you pick a vertex A, the eccentricity of that vertex is the maximum distance of any other vertex from that vertex. Okay. And so the maximum value of the eccentricity of a vertex is actually the diameter of the graph, not that's going to be too important. So we have this parameter eccentricity, right? And I'm going to get an eigenvalue bound on that. And the way we do this is sort of a standard linear algebra approach to getting bounds. You encode things into vector spaces, and then you say the set I'm interested in is linearly independent, and therefore its size can't be bigger than the dimension. And so this is essentially what we're doing here. So I need one more tool. So I'm going to define for a vertex A in the graph, I'm going to define the warp module to be the of A to be the span of the vectors you get by applying powers of A to the characteristic vector E sub A. So E sub A is the vector which is 1 on the vertex A and 0 everywhere else. Okay. Now, privately, I tend to think of things like E sub A as functions on the vertices, but you're free just to think of them as column vectors. And this E sub A is going to be coming back again and again and again in the course of the talk. So it's 1 on the vertex A, 0 everywhere else. Okay. And so the span of these vectors is a subspace, and clearly it's closed under multiplication by A. And so it's an A invariant subspace of the functions on the vertices. And so it's a module for the ring of polymers in A. That's going to matter much. And so we have a simple lemma that the dimension of the warp module is at least 1 plus the eccentricity. Okay. And the idea of the proof is simple enough. If you think about the vectors E sub A times E sub A squared times E sub A, you can imagine A is the first vertex of the graph. Now, when you look at A times E sub A, the only non-zero entries will be in positions corresponding to vertices at distance at most 1 from A. And when you look at A squared times E sub A, the only non-zero entries are indexed by vertices at distance at most 2 from A. And in particular, since there are vertices at distance 2, there will be non-zero entries there. So if you write down your vectors, E sub A times E sub A squared times E sub A, it's looking like a triangular matrix. Well, it's kind of triangular. Okay. And the nice thing about triangular matrices is the columns are independent. Okay. And so provided you're not too greedy and don't let the index k go past the eccentricity, you deduce that, well, in fact, what you deduce is that the vectors A to the j apply to E sub A from j equals 0 to the eccentricity are linearly independent. Okay, so therefore we have that eigenvalue bound. Now, since in general we don't have an easy way of getting information about the dimension of the warp module, it's not entirely clear how we've used this, but we'll see. Now, to get further, I need a tool, which again I'll be using again and again in the course of the seminar. So this is just a summary of spectral decomposition for a normal matrix. So you've got a normal matrix, assuming it's got distinct eigenvalues, θ1 up to θm. Then there are emission matrices E1 to EM satisfying those four conditions there. Now, the thing to bear in mind is this is really just a tidied up version of the fact that you can diagonalize normal matrices or symmetric matrices. So, and you can read off the claims here from those proofs. I'm not going to worry too much about that. I do want to explain a little bit of what some of those things mean. So if we apply, well, first thing is that E sub R is in fact the matrix that represents the orthogonal projection onto the Rth eigenspace. Okay, and that means each column of E sub R is an eigenvector for A with eigenvalue θr, and so you get the first equation. The second thing is that since the eigenvectors span R to the n, obviously the n where we're working, some of those projections must be the identity map, and that's that. Secondly, because they're projections, they're idempotent. That's the third claim. And the other thing is that if R and S different, then the projections are orthogonal in the sense that E sub R times E sub S is 0. Okay, so now we need a little more. We can actually write A as a linear combination of the E's, and I've done the calculation there. So that's the first line. And the important thing is actually the second display there, that if f is some function that's defined on the eigenvalues of A, a polynomial, for example, then f of A is equal to the sum f of theta r, E sub R. So we can evaluate functions on A very easily once we have the eigenvalues and the spectral idempotence E sub R. Okay. And so this is particularly useful when you want to evaluate a lot of different functions on the same matrix, and we want to do that. And I was saying here, one consequence is that the idempotents are actually polynomials in A, but I don't think that's going to matter today, so I won't say anything more about that. So the claim now is that if we, given the spectral decomposition of A, the non-zero, I can find an orthogonal basis for the warp module. Okay, and the basis just consists of the vectors E sub R applied to E sub A that are non-zero. Now, E sub R, E sub A is just the projection of the vector E sub A onto the eigenspace belonging to theta R. Okay, and so for each eigenspace, you've got a projection. Some of them will be 0, some of them will be 1. We'll take the non-zero ones. Okay, and then you observe a few things. First, that the E sub A is equal to I times E sub A, and I is equal to the sum of the E sub R's. So E sub A is a linear combination of these projections. Secondly, if you apply A to the K to E sub A, then you get sigma theta R to the K times E sub R, E sub A. And so now you see that the non-zero vectors E sub R times E sub A, the non-zero projections span the warp module. Okay, so the first thing is the projections span the warp module. The second thing is that the distinct projections are orthogonal, and the calculations there on the last line. Okay, the point is that E sub R, E sub S is 0 if R is not equal to S. And so you have an orthogonal basis. And now we'll be using some of this machinery again and again. I need to define one technical term. If I have a vector F, I define its eigenvalue support to be the set of eigenvalues theta R such that E sub R applied to F is not 0. So these are the eigenvalues where the projection is not 0. Okay, and so for any vector in a graph, I have an eigenvalue support. Now there's kind of a physical picture. If you think of your graph somehow as being some sort of three-dimensional rigid framework, and you drop it, then you'll hear a lot of banging and noises and ringing, and the ringing will be at different frequencies. And those frequencies will be given approximation just with the eigenvalues of the graph. Okay. Now, if you're more sophisticated, you have it hanging from a thread and you just tap on one vertex, you'll again get some ringing, and you'll see a set of eigenvalues. And that'll be a subset of the eigenvalues you see when you drop it on the floor. And so the eigenvalue support is what you see when you tap carefully at a vertex. Okay, so there is a kind of physical interpretation. Okay, but for our purposes, it's just, in a certain sense, we're going to be using spectral decomposition, and we're going to have vectors E sub r times E sub a, and someone on a 0, we want to throw those away. Okay, and so the ones that remain belong to the eigenvalue support. Okay, so yeah, I've gone too far. Okay, yeah. So now we can get the analog to the diameter number of eigenvalues bound. And it simply says that 1 plus the eccentricity is less than or equal to the size of the eigenvalue support. Because the size of the eigenvalue support is the dimension of the warp module. So by thinking about the eigenvalue support, we've got a bound for the dimension of the warp module in terms of eigenvalues of the graph. And so this is the analog for the number of distinct eigenvalues versus diameter bound that I started with. Now, if you replace the vector E sub a by an arbitrary vector F, you can generalize this in various ways, but it doesn't matter. So the point is we have this bound that the number of size of eigenvalue support is an upper bound on 1 plus the eccentricity of A. And by the end of this talk, we'll use this to do something for non-trivial. Okay, so that's the algebraic graph theory. So now I want to start talking about quantum walks. And quantum walks involve quantum mechanical systems. And there's an awful lot of stuff written on this at various levels and at various quality. There's an awful lot of things we can throw away as innocent graph theorists. So we're going to have a quantum system, which you can vaguely think of as a finite-dimensional vector space, complex vector space for our purposes. And the states of the system of dimension, I should add the D and N. Let's say a state of an n-dimensional system will be represented by n positive semi-definite matrices. Like there are 2 mistakes there, with trace 1. So whatever a quantum system is, okay, we have an n-dimensional system. It has states, and these are n positive semi-definite matrices with trace 1. Now, a positive semi-definite matrix with trace 1, this is called a density matrix. And the special case where the density matrix has got rank 1 is called a pure state, although that's not going to fuss us much. So 2 very simple examples of density matrices are there on the screen. They're positive semi-definite, they've got trace 1, and we'll be using them in some form or another. But you don't want to be thinking about if you took a course in quantum mechanics, that's probably not going to help you at this point. The idea is that the states are given by positive semi-definite matrices with trace 1. Now that's just linear algebra. People say that all the time, that's just linear algebra. So that's okay. Now I've got a little review of positive semi-definite matrices here. So first thing is just the definition. And a few remarks that a non-negative linear combination of positive semi-definite matrices is positive semi-definite. And a set of n by n density matrices, so that's positive semi-definite matrices with trace 1, that's a compact convex set, and its extreme points are the pure states, and 3 dimensions, you can draw a picture and call it the block sphere, and physicists are in love with it, but the precise statement is that the n by n density matrices form a compact convex set, and the extreme points are the pure states. And so if you had a bit of experience with playing with positive semi-definite matrices, this is all pretty straightforward. The thing we will need is that if you take a principal submatrix of positive semi-definite matrix, that's positive semi-definite too. And so in particular, what I need right now is that means that the diagonal entries of a positive semi-definite matrix are non-negative. Now they're non-negative reals. We're not requiring the density matrix itself to be real. Okay, it's got to be emission. That's part of the definition of positive semi-definite. But the entries are always, diagonal entries are always non-negative real. And this is crucial. So we have our density matrices and positive semi-definite trace 1, and the diagonal entries are non-negative and sum to 1. So it's a probability density. Now, okay, so I've described states. Now, that if you've got this quantum system, all you can do is carry out a measurement. Well, not all you can do. One of the things you can do is carry out a measurement. Now, there's lots of complications and lots of ink being spilled on what a measurement means, but we can avoid most of this. And in fact, since we're working in the context of quantum computing, we can simplify we use a very simplified version of measurements. So the first thing to bear in mind is if you've got this n-dimensional system and you carry out a measurement, then the outcome can be viewed as just one of the numbers 1 through n. So you can think of this as basically just being a dice with n faces. Okay, now maybe 1 mean spin up and 2 mean spin down, but the point is simply that as far as the measurements concerned, there are n possible outcomes. Now, what those outcomes actually are physically depends on the actual measurement you apply. But the point is that you've got an n-dimensional system, n possible outcomes. Now, the outcome, of course, will depend on the state of the system. Okay, well, actually the outcome doesn't depend on the state of the system. The outcome is one of the numbers 1 through n. You'll get the outcome I with probability equal to the II entry of the density matrix. This is a non-negative real number. The diagonal entry sum to 1. So you have a probability density defined on the outcomes. And the ith diagonal entry of D tells you the probability that when you carry out your measurement, you get the ith outcome. Okay, so this is a bit of a simplification, but it's all you need from most of quantum computing, or for an awful lot of it. So we can, and so there are ways of making it more complicated, but basically you've got your system, it's got dimension n, you've got your density matrix, you do a measurement, you get one of the outcomes 1 through n, and the only real information the experiment is giving you, well, quantum mechanics is predicting the probability that you observe a particular outcome. So in a sense, the outcome of the measurement is a probability density rather than a specific result. But anyway, you don't need to worry about that. But so the key thing, as I said, is the diagonal entries of the density matrix give you the outcome when you carry out the measurement. Now, for those of you who know more, you realize I'm actually measuring in the standard basis, but we don't need to worry about that because we can always arrange to do that in this context. So that's well and good. So I've talked about what a state is, and I've talked about what a measurement is giving us. And I made a mistake saying all you can do is measurement, but of course you can't. You can also change the state. And so we now need to describe how you do that. Now, change of states are manifested by using unitary matrices. So you apply an n by n unitary matrix to your system. Okay. Now, because I'm working with density matrices rather than vectors in some space, my transition look a little bit more complicated, but still I have a density matrix and a unitary. And the effect of applying that unitary to my quantum system, that's an experimental operation. The new state will be equal to u d u star. Okay, so we have the states. Okay, we've worked out what the measurements do, and now we're saying that we change state by, or state is changed by the application of a unitary. Okay, so you start with your density. The new density, according to this rule, is u d u star. Now, a couple of things to just notice is that u d u star is quasi-semi-definite. It's similar to D and the eigenvalues that a matrix quasi-semi-definite if only if its eigenvalues are non-negative. So u d u star is quasi-semi-definite, and the trace of u d u star is 1, or trace of D. So the effect of applying u is to transform your density matrix D into a new density matrix. And this is absolutely essential. If you didn't get a density matrix, you've done something wrong. Okay, so again, well, you can argue that 95% of basic fundamental quantum mechanics is just linear algebra, and so you don't need to be looking for deep and Schrodinger's cat hiding in the background or something. There's no cat pictures today. Sorry, Harmony. Now of course, if you apply your unitary matrix, then the implication is that you've got some state D that you know about. fact, sometimes you don't. You just say, well, if the initial state was D, then the new state is U, D, U star, and then start thinking about that. But the setup we're dealing with will generally have a fixed initial state, and it's going to be the density matrix of the form E sub A transpose. Now that's just a diagonal matrix with a 1 in the A position and 0 everywhere else. It's quasi-semi-definite, traces 1 is the density matrix. And most of the time, these will be the density matrices we'll be starting with. So the idea is we're going to be looking at a system where the initial state is given by one of these vertex states, D sub A, and we apply unitary, okay? And then we do a measurement. Now the point is your experimental process may involve a number of operations, but each of these is given by unitary. And so the composite of all these is just unitary. So you don't normally need to break things down into more than one hit. So we have our initial state and we apply unitary. Now, in this case, okay, so we've got our new unitary and I want to work out the probability that I get a given outcome. So I need to get the diagonal entries of U, D, U star. And what that calculation in the display line there is doing is giving you those diagonal entries. So I want the BB entry of U, D, U star. And when you, the point that, well, EB transpose U, EA is just the BA entry of U. And so you get eventually that the BB entry of your new density matrix is just the square of the absolute value of the BA entry of the unitary. Okay, so, and in a sense, in terms of quantum mechanics, all we can do is, work out what probabilities are and say this, make comments about probabilities. All the information we need is contained. This tells us all the information we need is got by looking at the squared absolute values of the entries of U. So if we're going to start in some vertex state, D sub A, and then we're going to measure the way I described, then all the information that we can talk about is contained in the matrix form by taking the squares of the absolute values of the entries of U. Now again, at this point, this is still just linear algebra. Okay, the interpretations are complicated, but the point is to get somewhere to work things out, I just need squares of the absolute values of entries of U. So since this is very important, actually I'll get back to that in a minute. I'll give it a name, but not right now. So finally, I can set up quantum walks. So if I have a graph with a density matrix A, now what I'm going to do is I'm going to use A to give me some unitaries. And in fact, I'm not going to go one unitary at a time. I'm going to have a one parameter family of unitaries. So I'm going to define U of t to be x of ITA. Now, physicists will put in minus ITA, but it makes no difference to anything you calculate, so I'm not going to bother. Now, we define x of ITA. We can define it in two ways. You can use the power series for x, or you can use spectral decomposition, and I'll talk about both those. But so U of t is a family of unitary matrices, and we refer to it as a transition matrix of a continuous quantum walk. Now, the physical image is we have some system that's initialized, so the state is D sub A, and then we're going to let it run for a certain time t, and then we're going to carry out a measurement. Now, the properties of the modified system are going to be determined by the matrix U of t. Okay, using the formula on the previous slide. Okay, so we call U of t the transition matrix of a continuous quantum walk. And there's a concrete example there. If you take the graph to be K2, then it's not too hard to expand the x of ITA by the series, and you get that U of t is equal to cosine of t, I sine t, cosine t. So you have an explicit formula. Okay. Now, it's physically meaningless to ask questions about the entries of U of t. The physically meaningful questions, the things you can actually observe, have to be stated in terms of questions and the squares of the absolute value of U of t. But I'll come back to that. But the point is, there's U of t. That's a unitary matrix. You also see that it's symmetric, which is you don't normally get your matrices to both unitary and symmetric. And dealing with complex symmetric matrices can be a little tricky from time to time. But it's a symmetric unitary matrix, and So as it should be. Okay, so let's go on. So the first 2 points I've already said. The third point there is that we can use the spectral decomposition to compute U of t. It's a function of A. Okay, and the spectral decomposition tells you that U of t is equal to the e to the it theta r times e sub r. Now, this is generally a lot easier than trying to use the series decomposition, the series expansion. Just think you're trying to work this out for the path on 11 vertices, for argument's sake. So you can get use the spectral decomposition. I should also say that we do a lot of computations related to quantum walks, and we're using this formula again and again and again. So you can use it numerically. That's important. And the other comment, the summary, is that if we had an initial state of walk as d sub a, then the probability that we observe outcome b at time t is given by u of t b comma a absolute value squared. Okay, so we have that. So, and again, at this point, you can more or less forget about the physics. We've got everything translated out in terms of matrices and eigenvalues. The only thing is messy is that, generally speaking, linear algebra, you don't start taking squares of absolute values of entries and then start trying to ask how that matrix is related to the original matrix. But it's all entirely linear algebra. There's no entanglement to worry about. There's nothing, you just have these formulas and you're trying to derive consequences. Now, if you understand the physics, you may be able to predict some consequences or expect some consequences, but we don't have to have it. And since I'm going on about these squares of absolute values, it's useful to define the mixing matrix of a walk. And so the circle there is the Schur product, entry-wise product of the two matrices. And I'm implicitly noting there that the complex conjugate of u of t is u evaluated at minus t. And so the mixing matrix, well, its entries are non-negative real numbers. And since they're the squares of the absolute values of the entries of u, or ut, now u is unitary, so the sum of the squares of the absolute values of the entries of u of the row of u of t is 1. And the sums of and it's symmetric too, and so the sums of well, it doesn't matter, the sums of the squares of the absolute values of the entries of a column of u of t are 1. So M of t is a symmetric doubly stochastic matrix. Each row is entries in each row are non-negative and they sum to 1. Entries in each column are non-negative and they sum to 1. And the important thing here is if you look at a column of, say, the A column of M of t, that's giving you the probabilities of the various outcomes if you measure at time t, given that you started at A. So all the information about the quantum walk is contained in M of t. Okay? And so it's an interesting matrix, and it's got various uses, some of which we might see. The thing now is to start looking at some examples. Okay, so here I've gone to all the trouble of working out, dealing with the path on two vertices. So I've written down M of t, and we've got a new proof now that cos squared plus sine squared is equal to 1. Okay. And what I've plotted here, you can think of as the probability you start at vertex at, say, 0, and I'm measuring the probability that, well, I'm giving you plotting the probability that when you measure, the result is 1. So you can think of this as, you want to think of this as something like a classical random walk. Then you could sort of imagine, well, we're starting at 0 and asking what is the probability I'm on 1 at time t. Now, I don't entirely like that interpretation. I'll come back to that, but that'll do for the moment. So, so particularly, it's a little tricky to see, but this peak here is at time pi on 2. Now, at time pi on 2, cos squared is 0, sine squared is 1. So you get 0, 1, 1, 0. And so if you look at this 0 column, you have 0 over 1. And so that's telling you that when you do a measurement at time pi on 2, given that you started at 0, you will always be at the state 1. Okay. Now, the eigenvalues of the path on two vertices are integers, and so it follows from this that u of t, the transition matrix, will be periodic, and so that's manifesting the rest of the picture. So it's a perfectly nice picture, and we're seeing some interesting things happening already, okay? In particular, that we're getting this, if you start on vertex 0 at time 0, then at time pi and 2, you're on vertex 1. And this is actually important, but we'll come back to that. So a few things you can observe from this. At time pi, M of t is the identity. This is generally called periodicity. Time pi and 4, the matrix M of t is just 1 over 2 times your 1's matrix. And the technical term here we use is uniform mixing. I won't be talking about that today, so we'll go on. And the other case where I did talk about is at time pi and 2, and M of t has that form. And this is giving us what we call perfect state transfer. And I'll come back to that in a little bit. That's what, in some sense, that's what we're really on about, and we'll come back to that. Okay, so we've done the path on 2 vertices, so let's get a bit more ambitious. Now we do the path on 3 vertices. And you could probably do this by hand too, but so there's a peak there. It's not obvious in the picture. This is at time pi and root 2. And at that time, you're getting probability 1. So this is a path on 3 vertices, but what this is, and I'm looking here at the probability that you're on vertex 2, you're starting at vertex 0. So at time pi and 2, if you start at vertex 0, then you're on vertex 2 with probability 1. And so this is another example of what I was calling perfect state transfer. Okay, and again, it's periodic, and so that's lovely. Okay, so now we get cocky and go to path on 4 vertices. Okay, now, if you stare at that for a while, it starts to look regular and symmetric and stuff, but I mean, it's not. If you look at, I guess it's about 28, there's a peak, and it looks very close to 1. And it is, but it's not equal to 1. Now you can continue this plot. You know, I've only gone to 50, you can go to 500. It doesn't look, the individual piece length 50 don't look that much different. And there'll be peaks that look close to 1. And so one question you might ask, well, does it ever get to 1? So if it gets to 1, then at that time I have what I was calling perfect state transfer. I know that if I start at vertex 0, then at that time I'm focused on a particular vertex of the graph. Turns out you can show that you get arbitrarily close to 1, but you never reach it. Okay, that's cool. No, we won't go into that today. Now, just to make it even clearer, or less clear perhaps, this is the plot for the path on 11 vertices. Now, this peak here, there's a peak here at about, well, after a very long period, you get a peak around 0.9. What happens in this case is there's an upper bound, or with a positive epsilon, and the probability of being on vertex 11, given that you, vertex 10, given that you started at 0, is always less than 1 minus epsilon. So you don't get perfect state transfer, you don't get even a good approximation. Okay. And so you see that there's a range of behavior, and starting from simple to more complicated, and we're just looking at paths. So, summarize what we know. The only paths that admit perfect state transfer are P2 and P3. Okay. And a nice open question, which has annoyed me for a long time, is whether there's a tree on more than 3 vertices with perfect state transfer. Now, trees aren't that much more complicated than paths, really. The first result is sort of really being common. Number of people have proved versions of it, and so I won't go into the history of it. But we have that question. We do know, this is I think this is very hard, at least we've been stuck on it for a long while. I think it's very interesting. We have a bit of partial information. If we have a tree on at least 3 vertices, now we've been using the adjacency matrix, but there's nothing stopping us really using any linear combination of the adjacency matrix and the diagonal matrices of valencies. So in particular, we could use a Laplacian in place of the adjacency matrix. Now, it's pretty natural. There are papers by physicists using Laplacian. And Gabriel and Henry Liu proved that if you're using the Laplacian, in place of a matrix, then you can't get perfect state transfer on a tree with more than 2 vertices. And Godsil also proved that if the adjacency matrix for a tree is invertible, then perfect state transfer doesn't take place. Now, this is kind of good news and bad news. Most trees don't have invertible adjacency matrix. On the other hand, I still have this feeling that's probably the best place to sort of try and attack, so to try and weaken the invertibility condition and sort of produce classes of trees where we can rule out perfect state transfer. Now, before I go on, I should say perfect state transfer is quite important physically. There's a theorem theorems, that's why they have theorems in physics. A theorem in physics called the no cloning theorem, which basically tells you can't copy a quantum state. So if you've got a quantum system in a certain state, you can't produce a new quantum system in the identical state. One of my students once described this by saying is the photon copier breaks down. Okay, so you can't copy a state. Now, if you're trying to run a computer, then you need to store states, and you'd very much like to be able to copy them. But you can't. But the point about perfect state transfer is if you have perfect state transfer, as I've described it, then you can, what's happening, you can, in a certain sense, transfer the state of a system from one qubit to another. Now, this is a little vague because, and I'm not going to go into details, but so the point is that if perfect state transfer occurs, it does allow you, it does provide you a substitute for copying. Let's put it that way. Okay. And so from that point of view, there's been considerable interest in terms of quantum walks. A lot of the discussion was based on whether you could get perfect state transfer or not. I should say that if you have perfect state transfer on a graph, you get perfect state transfer on its Cartesian powers. And the Cartesian powers of K2 are better known as the cubes. And so if you have a D cube, then you can get perfect state transfer from any vertex to the unique vertex at distance D. So you have infinite families of graphs with perfect state transfer. Okay, so there's the question, is there a tree with perfect state transfer? Now, the point about a quantum walk is that in general, it's not recurrent. Okay, if the eigenvalues of the adjacency matrix you're working with are integers, then yes, it is recurrent, but in general, that's not the case. And so in general, the walk's not recurrent. And in general, if you look at something like the path 11 vertices, the picture is pretty messy. Okay, so are there any, the other point, of course, is that in a standard classical random walk, under mild conditions, things settle down to a steady state. Now that can't happen with a quantum walk. Okay, so, but there are a few things that we can do and say. And so I want to, okay, so, well, what I'm going to show is that quantum walks are, in a sense, recurrent. So a bit of notation, I'm just going to use angle brackets m comma n to note the standard matrix inner product. And so the norm of m will be square root of the m comma m. So m comma n is just the sum of the squares of the absolute values of the entries of m. Okay, so that's just notation around that. And the theorem is, well, that quantum walks are periodic. Okay, and so there's a statement. So you give me a positive epsilon and a positive real number tau. And then there's an integer k such that at time k tau, u of k is within epsilon of the identity. Now, this means the walk is repeating in some sense because you've gone back to identity and you're very close to identity. So if you repeat things again, you're going to get a very good copy of what you first thought. So so from one point of view, this is actually very interesting. The physicist will turn up their nose because there's no useful bound on K, and it tends to be very large. So if you want to demonstrate this by an example on the path on 4 vertices, you're going to need K to be about something in the order of several hundred times pi. And so there's a question about physical significance, but still the point is that these walks are recurrent. We do have this, and I'll sketch the proof. This is really quite simple. You've got a sequence of matrices, UK tau. This K is 1, 2, 3. Okay. Now it's a sequence of matrices in the unitary group, and the unitary group is compact. U star U is equal to identity, so it's compact. So you've got an infinite sequence in a compact set, so it's got a limit point, which I'm going to call M. Now, since it's a limit point, if you pick any real number, let's say epsilon over 2, and there are infinitely many points of the sequence that lie within epsilon over 2 of M. I'm not going to be greedy, I'm just going to take 2 of them. So U tau and UM tau. Now, since they're each within half epsilon of M, they're within epsilon of each other by the triangle equality. And so you get the, and so that gives you the value of K. It's M minus L in this case. Okay. So the point is, this is the only thing which that stops you doing this undergraduate course is you don't want to talk about the unitary group being compact, I guess. But I mean, it's nothing, it's really bogs down to calculus. And you're getting a fairly strong conclusion. Now, it's possible to strengthen the conclusion, but I won't go into that at all. The other thing I want to comment I want to make at this point is in working with quantum walks, well, you've seen lots of eigenvalue stuff in spectral decomposition, and we'll be actually seeing some number theory creeping in very soon. And what we're doing here is basically we're using ergodic theory, at least that's up to my limited understanding of ergodic theory, to get qualitative information at what's going on in a quantum walk. It's the time. So actually, I'm going to jump ahead. So I tried to convince you that perfect state transfer was useful and interesting. And now I want to show that it's actually hard to find. There's not many examples. So to do that, I want to derive some conditions of perfect state transfer. Now, I said that if I'm in a system with an initial state D, then the new state after I apply U is UD U star. Okay, now I'm going to be applying UT du, U of minus T. And the point is I can express U of T using a spectral decomposition. And so I can get a very useful formula. So if I say that the state at time T, given that I started at D sub A, is D sub A of T, well, that's equal to U of T, D sub A, U of minus T by definition. And now I can expand or replace U of T and U minus T by their spectral decompositions and do a bit of arrangement. When you do that, what it boils down to is a sum of pairs of eigenvalues, the IT, theta R minus theta S times ER D E sub S. Now that doesn't look particularly pleasant, but it turns out we can do quite a bit with it. So let's just go on. So we have an expression for so in other words, I have an explicit expression for U of T, D, U of minus T, using the eigenvalues and the spectral eigenvalues. And what we can deduce from this is a number of things. Is that if we have perfect state transfer from A to B, then A and B have the same eigenvalue support. Remember that, okay. The second condition, which is quite important, although I won't be going into today, is if theta R and theta S are in the eigenvalue support, then those two matrices there, E sub R, called D sub B, E sub S, and E sub R, D sub A, E sub S are either equal or minus 1 times the other. Now, this tells you a number of things. It tells you that the squared lengths of the projections of E sub B and E sub A onto the theta R eigenspace have the same length. In fact, they're either equal or opposite. So this is quite important in practice and for other purposes, but not today. The other thing we get is that if we have 4 elements of S, then that ratio there is rational. Now, and that condition, that condition ratio must be rational. It's called the ratio condition. It's due to Saxeni, Severini, and Sparlensky. Now, the thing to bear in mind is the eigenvalues of graphs in general are not rational. algebraic, and they're algebraic of fairly high degree of complexity. I mean, it's almost certainly true if you pick a graph at random that the character polynomial is irreducible over rationals. Okay. And so that condition there is quite a bit stronger than it appears, and we'll see an example before very long. So how do we prove this? Well, if we have perfect state transfer from A to B at time tau, then we get that formula there for E sub B transpose. Now, the nice thing about the E sub R's and the E sub S's is they're pairwise orthogonal. So if I multiply that expression on the left by a particular E sub R and the right by a particular E sub S, I get the second equation there. So I've got E sub R, D sub B, E sub S. Well, that's just a real matrix. And on the right, I've got that exponential, and then I've got E sub R, D sub A, E sub S. Well, that's just a real matrix. So that tells me that that exponential there must be real. Okay, and if that's real, we just use Demar's formula that tells you that sine of theta r minus theta s times tau must be 0. Okay, now this is kind of interesting because we're talking about perfect state transfer between vertices, but that argument I've given you doesn't really put much restriction on the states. It just says if the initial state's real and the state at time tau is real, then you're getting the ratio condition. So it's more general than it appears. But anyway, all we needed is that both eigenvalues are real. That exponential is real. It follows, of course, that if the exponential is real, if the sign is 0, then exponential is plus or minus 1, which was one of the facts that I had on the second, more or less the second line there, second display there, whatever it is. Now, so we've got this ratio condition, and just to give it a little bit of weight, the eigenvalues of Bach on 4 vertices are as written. I can't see any typos there. And so I now take the, it's the first minus the third over the first minus the second, and I get root 5. That's not rational. So that proves that I can't have perfect state transfer on a path on 4 vertices. So some fairly simple number theories are giving us quite a strong conclusion. And the problem in a sense is to generalize this and to rule out more graphs. And the tool I need is the following theorem, that if you have perfect state transfer from A to B, and the eigenvalue support of A is S, and that's going to be the eigenvalue support of B as well, what that matters. And if theta R and theta S are distinct elements of the eigenvalue support, then their squared difference is an integer. So the ratio condition just tells us the ratios of certain differences are rational. But now we're getting a stronger result. We're saying that a certain squared difference is an integer. Okay. And this involves some field theory, and I'm going to drag you through it briefly. The first comment is that by Godsil theory, well, what I'm going to do is I'm going to take my ratio theta r minus theta s over theta k minus theta l, and I'm just going to write down all the ratios for all possible k and l, with k and l different, and multiply them all together. So in the numerator, I'm going to get a power of something, and in the denominator, I'm just going to have a product of differences. That product of differences is a discriminant, and well, actually, that doesn't matter. By Godsil theory, that product of differences must be an integer. So the product of the denominators there must be an integer, and the exponent, well, it's just an nth power of theta r minus theta s. So that means that theta r minus theta s dm is rational. But on the other hand, theta r and theta s are algebraic integers because they're eigenvalues of the character polynomial of a graph, and they're integer polynomials. So they're algebraic integers. And so the only way you can be rational and an algebraic integer is to be an integer. So theta r minus theta s to the m is an integer. Now, well, the argument is that as all algebraic conjugates of an eigenvalue of a symmetric matrix are real, you actually can deduce from that not just that theta r minus theta s to the m is an integer, but theta r minus theta s squared is an integer. Okay. So, I mean, if you write out this proof with more details, it'll cover more real estate, but that's the gist of the argument. And it illustrates, as I said before, one of the features of working with quantum walks is that you do find yourself some non-trivial number theory coming up and being useful. In other places, we've used the Goldfein-Schneider theorem, for example. So it's not just this exception. And the conclusion now is that there are only finitely many connected graphs with maximum valency k that admit perfect state transfers. So this would tell you that there's only finite many paths that admit perfect state transfer. And so let's go think about, well, we've done all the work. Suppose you've got perfect state transfer to vertex A and X, and the eigenvalue support is X. Well, the first thing is just in spectral graph theory, the absolute value of any eigenvalue is bounded above by the maximum valency. Okay. The second thing is we know that theta r minus theta s. If theta r and theta s are in the eigenvalue support, then their square difference is an integer, and so the absolute value of the difference is greater than or equal to 1. So that tells you that the eigenvalue support can't be too large because it's got to consist of a bunch of eigenvalues between minus k and k, any two of which are at least 1 apart. And so when I do it, I get an upper band of 2k plus 1 on the size of the eigenvalue support. But that means I have an upper bound on the eccentricity of vertex A. So every vertex in the graph is a distance at most 2k from vertex A, and the valency of the graph is at most k. And so therefore the number of vertices of the graph is bounded by a function of k. And that's the